Myself, Altaf Mansuri. I am from Innovative Engineers, India. Thank you for organizing this virtual expo in this pandemic situation where we can interact with each other and exchange ideas and business possibilities. Our company, Innovative Engineers, is at Ahmedabad, city of Gujarat. We are having more than 20 years of experience in designing and execution of clean rooms. We have served top clients of India and now serving to Asian and African countries. I thank you for the opportunity given to me for presentation on clean room concept design. Now I am sharing my screen so that we can start the presentation. Just a second. Yes. So, friends, as I said, our company is Innovative Engineers, and our topic is today clean room concept design. Now, as we all are aware that types of pharmaceutical plants, we have two types of pharma plants. One is OSD, it is oral solid dosage, and the other one is injectable plants. So these two are the major plants of types of pharmaceutical plants, and which will be there in our discussions today. Now, the which services are critical in designing in any clean room? So there are two services. One is air, which is very critical part in designing, and the other one is water. So this in this concept design, today's topic we are going to discuss the how can we design the air in both types of pharmaceutical plants, that is OSD and injectable. Now, in designing of air, which is very critical as I mentioned earlier. So the in air we have to design to control the following parameters like temperature, relative humidity, pressure gradient, cleanliness, and cross contamination. Now, in temperature and relative humidity, it is different in case of different type of applications and the product used. For example, somewhere it is 17 degree, 19 degree centigrade also, and with the RH of 55%, 60% relative to temperature. And somewhere it is 21 plus minus 2 degree centigrade and 55% RH based on the product requirement and the process requirements also. Pressure gradient, again, it is different for the OSD plant and different for the injectable plants. It can be designed in, I'll show you in the next slide. Class of cleanliness, again, it will be different for OSD and for injectable plants. For OSD plant, it will be little lower class like class D, and somewhere it is class C. But for injectable plants, it is class of cleanliness will be higher like class B, class A. That we will discuss in upcoming, I will show you the brief in layouts also. This is very important aspect is cross contamination. Now, cross contamination in case of OSD is very critical. We are designing, we'll show you in the upcoming layouts. The air cross contamination is avoided based on the pressure gradient. This is a third point, very important point. It can be controlled like that. I am showing you in the further layouts. This is a oral solid dosage, temperature, and RH zoning layout. You will see that these areas which is marked in blue as well as in green, these areas are the main process areas. So these areas are generally designed at 25 degrees centigrade, not more than 25 degrees centigrade, and 60% humidity. Their support, their immediate airlock, personal airlock, and material airlock. These areas are designed only for temperature. Humidity, again, you can mention as not applicable. The other support areas which are marked in green, again, these are designed as temperature for 25 degree centigrade. And store areas where your product is packed and to be stored, you have to design that product areas at 27 degree centigrade. Now, These temperatures are generally designed at this temperature and humidity. If any specific product requirement are there, then it can be changed accordingly. Now, if we move to same OSD plants, OSD plant, now how the pressure gradient will move in oral solid dosage plants. You will see that the main production areas, like for example, we have shown here, it is compression, this one. So these areas are negative and their immediate airlocks. You have seen there are two airlocks, one is personal airlock and one is material airlock. So these airlocks are positive pressure airlock and their positive pressure will be higher compared to the production areas, and it will be again higher than the corridors also. So these are at, for example, if we talk of the values, then for 45 Pascal is for the person and material airlock, 30 Pascal is for compression, and again the 30 Pascal pressure for the corridor. So you can see that these airlocks are acting as very positive. We generally we do the terminology as a bubble airlock. So the pressure from both the airlocks move from to corridor as well as the compression. So there will be this particular design will avoid you from the cross contamination. No air from these production areas, process areas will move from here to the main corridor, and it can move, it cannot go to the other process areas. So this is very critical while designing any clean room. So in these cases, your production rooms are negative. This is a typical airflow diagram, schematic diagram for oral solid dosage plant. Now, this particular drawing it will show you how many types of filtrations are used in any OSD. So there will be a fresh air and return air inside the AHU that will have primary filtration of 10 micron. Then secondary filtration will be of 3 micron, and terminal filtration, that is we called as the first quality of air, it will be 0.3 micron. In risers, return air, in OSD plants, it is we put at 10 micron filters. It is just to safeguard the return air ducts and the loading of the AHU filters. This is how we safeguard that. And in particular, OSD plant, the process area AHUs like compression, granulation, the bleed air which is shown here, this is bleed air is exhausted with a HEPA filter. So this HEPA filter will ensure that whatever bleed air we are exhausting will be through HEPA. So that is also to avoid any contamination in the atmosphere. Now, if we move to injectable plant temperature and RH zoning. Now, this is similar to what we have seen in OSD plant. These are the process areas. You can see these are designed at 25 degrees centigrade and 60 to 65% RH. Here RH flexibilities are there in production areas in case of injectable plant. Temperatures, because there are so many multiple airlocks, you can see. In OSD, we have seen only one material airlock and one pan airlock. In injectable, we have 6 airlocks. So this is for the double gowning procedure. So for these double gowning is there. So sometimes it is mentioned and it is designed as at 21 degree plus minus 2 degrees centigrade also. But the maximum limit is NMT 25. So this is how the injectable plant temperature and RH zoning looks like. The other areas and support areas are also designed at 25 degree. Airlocks are designed at 25 degree and RH not applicable. The other supporting areas are designed at 25 degree and 60 to 65% RH, and the change room and other areas are designed at 25 degree centigrade. Now, this is how the injectable plant pressure gradient looks like. This is absolutely reverse than the what we have seen in case of oral solid dosages. You can see that the topmost highest pressure areas will be manufacturing areas or filling areas, ampoule filling and vial filling, these areas. These are the highest pressure areas, and from here the air will come out. Sorry. I'm sorry. From here, the air will go out. In case of OSD, it was reverse. The air was coming in. So in these case, air goes out like this and it goes out to the corridor. Now, so this design in our terminology, it is called as a cascade design, wherein the highest areas pressure is in manufacturing area, and it goes out from manufacturing area to sterile corridor to the airlocks, then the external corridor and change room, and it is out. So this is how it is being designed. It is exactly reverse than the OSD plants. This is a typical injectable plant airflow diagram, wherein you can see that these airflow diagrams you are seeing that one more filtration level is added other than the OSD. One more HEPA filter inside the plenum is added, because in these areas you have to maintain higher class. It is class B, and in some cases it is class A with LFs also. So in that case, the HEPA filter loading, we have to avoid dust loading on the HEPA filter. That's why this one more HEPA is added. We call sometimes it is F9 or sometimes it is H13 also. So we have in this case, we have 10 micron in fresh air, 10 or 5 micron in the secondary air. This is 3 micron, again 0.3 micron, and again in the first quality air, it is 0.3 micron terminal HEPA. Then it is written air is collected and sent back to the A tube. So this is how it is very critical. In case of injectable plant, the filtration levels are very critical. The fans particularly will be high static fans. We have to design to take care of double HEPA filters, pressure drop, and fan motor selection has to be very critical in case of injectable plants. Now, what qualification test we have to carry out? This is a brief details about that. While installation of the air conditioning systems, HVAC systems for clean room, the duct leak testing is to be done based on the classification of the area. For example, as I discussed earlier about the pressure testing of duct as per the class A, class B, class C. So on that basis, we have to do duct leak testing, and the duct leak testing methods and standards are also specified like DW142 and SMACNA standards. So based on these standards, we have to follow this duct leak testing. Then the second test, once the installation is completed, we are about to start the qualifications. Once the HEPA filters and all filters are placed in the system, then we can do the air volume measurement for all rooms. We have to measure the air quantity and we have to compare it with the design quantity, and we have to achieve those quantities that we call air changes per hour also. The third test is once the air quantity measurement is done and it is set as per design, as per DQ, what we say, design qualification, then we do the HEPA filter integrity test. Now, HEPA filter integrity test, in that we do two things. One is the media leakage and other is the site leakage portion. So that is being carried out once your all HEPA filters are installed and it is put place, and once air quantity measurement is done. So generally we designed all HEPA filters and all these things around 90 fpm to 100 fpm, so there's to maintain laminarity and to get the desired results of the defined classes. Once that is done, we do particle count test of the area as per it is classified. For in case of OSD, it is class C or class D. In case of injectable, it is class C, class D, and some classes with LF, it is class 1 also, class A also, sorry. So once these particle count, it is passed and it is following the results as per ISO guidelines. ISO 144 is the guideline, 14464 is the guideline. If that particle count results are falling within the limits, then it is considered as it is a qualified area. Generally, we design at 25 to 30 air changes per hour to achieve particle count in case of class D for OSD plants, and generally we design in terms of, in case of injectable plants, 60 to 90 air changes power based on the clean room construction of the walls and ceilings to achieve the class B and class A along with the laminar airflow units. After particle count test is done and it is established, we do area recovery test, and that based on that area recovery test, we can estimate the recovery time of any system due to, if for example of any system is in failure of or not in operation, how much time it takes to come back to the system in the qualified manner. So that is why the area recovery test is conducted of. So it depends on the area and dust loading and everything. Sometimes somewhere it is 5 minutes, somewhere it is 6 minutes. It depends on the size of the volume and the dust loading inside the room. The last is pressure balancing. Now pressure balancing, as I said you, is for OSD it is different, for injectable it is different. So pressure balancing, as I informed you, it is bubble airlock kind of design. We have to do pressure balancing that way, and we have to set that way. For injectable, it is cascade design. The highest pressurized room are the production areas. Nowadays, we can monitor these pressures along with temperature and RH, along with the digital devices also, and it can be monitored through a central stations also. The temperature and RH, again, it has to be controlled through a PID controller, and which can be again monitored through a central station, so that you can easily do the recording, data mapping, and you can show it to the auditors and the required authorities. So temperature, RH, and pressure, these are the three parameters which you need to do online monitoring to show it to the auditors. Balance all these states. Duct leak testing is one time. HEPA filter is every 6 months. This is again at 6 months. Area recovery and particle count is again for 6 months. Now these are the videos of some of our site for validation. This you can see. See, this is the airlock for the OSD plant. You can see that air is coming out. It is positive pressure from material airlock. It is coming out to the corridor. This is OSD plant. The another video we have, this is showing you that your AHU blow. One more video we have, it is showing you for the risers. This is a riser, low level return, and you can see that air is going inside the riser. So these are the smoke pattern test which is generally conducted at the end of the all validations are done with room numbers marked, grid numbers marked, supplier grills are marked. Now I would like to thank you so much for the opportunity given to me for this presentation, and in case of any questions and any queries, please feel free to contact us. Our contact details are available. I can be contacted at these details, and these details are also available at our Expo at stall. We will be very happy to reply you to your queries and question and answers. Thank you very much once again. Thanks a lot. Good evening.